see, it's there. Okay, so let's get started with some lectures on, as said, transverse momentum distribution functions and beyond, nucleon, tomography. Was more or less a combination of some issues given to me, and even that title was slightly different I saw on the outside. So it is a number of aspects that I want to treat. Not after thanking the organizers for giving me the opportunity, because that's something I like to do. I mean, I know most of you are from not too far. Most of you are from Italy or working at a university in Italy. Now, let me immediately show you 2 slides down. If it, I mean, this is an abstract, we'll come to what we are doing. One of the nice things is, oh, wait a minute, there was supposedly, let me go back. I wanted to show you this, because I'm proud that Andrea Signori and Sabrina Cotogno also got their education here in Italy, and right now are 2 of the 4 PhD students I'm working with. So in that sense, I hadn't even a chance to confront Sabrina and Andrea and Tom, who are the newest one. Martin is already more or less finishing this year, and actually next year we'll go to Daisy. So he knows most of it, of what I'm going to tell you. Actually, some of it he did the work, the real work. So that's because usually if I go into details, it refers to things I've been doing myself. And that's also what I think you should do. At some point you should really sit down and do these exercises. Mike already gave you a number of exercises, and actually they fit very well in with the ones I'm going to give you. So that's I'm going to give you some of that material. Let me go to another thing. These slides I will also make available and put them on my my homepage, or maybe on the Institute's page. This already may be there somewhere. That's this thing. So let's make that full screen view. There should be something like full screen. Let me, yeah, full screen mode. No, that doesn't that doesn't help much. Nevertheless, this is most of you have here access to the computer. So this is not what you read. What I'm anyway going to use right now. I want you to tell it is available. It's so the better way to do it is to do escape, go to this thing, make it. What is it? 200%. Let me do that. Make this thing big. I mean, is it? I mean, this takes time, but it doesn't matter. I mean, after the previous lectures, you will be in for some relaxing or so, huh? But see, so this is already much better. So this is available also to you either through the web page as it already. But I I already this morning put in a new version on my homepage, so there you find the latest version, because I will keep on working on this also, because usually such a series of lectures is a very nice opportunity for myself to, at some point I see you glazing or so, and then I think there should be either something or we should, or I see, here I forgot to explain something, and then I'll add it to it. So as I'll scan through some of this, so let me put in this, then I think I can go on. So there's an abstract, there is an asset set. it's a very preliminary working document for lectures presented here. It's actually many of them, or most of some of the material you can find back. There were some lectures I gave a few years ago at the Varenna school, the Fermi school in Varenna. Again, Fermi seems to be have been everywhere in Italy, but at the Varenna school, so some of the material is taken from those lectures. Some of it is taken from lectures I gave in Taiwan last year. So there's lots of, and that makes it a little bit chaotic also if you look at it. Particularly at the end, it becomes very chaotic. There's some appendices and you think, what have they to do with? And maybe they have nothing to do with it. So keep on reading in the beginning, and I'll during the week, build up the document even more. So you see there's lots of material, and if you go there, and I'll start off here with some of the things, with this, at some point here, when is the first one? Here, there's an exercise. And to make it easy for you, I put in the answers also. So if you continue here, the answer is also there. So, but not always. The answer is here, and sometimes the answer is simply, here there's an example, I think. At some point, here there's an exercise, there's no answer. Actually it is such a thing, do a particular Lorentz transformation. This is an example of, now you have to do that at some point for yourself. The answer is there, and I think everybody, I mean, it does make sense to put in the 3 equations which are in between, or the check that you have to do. But I will help you to see what you have to check at least if you ask me. Yeah, so that's a bit of sort of material that you can start using, and that is directly related to and will be built up depending on also your input, your questions. So let me put that thing down again, and let me here. Yeah, again as an intro. So let me see, the previous one was this. Yeah, so let me as an intro follow a little bit on continue on the way Mike started, and before going to do some things more explicitly, show you that I mean there are simple things. Actually, it looks like it's running even. Isn't it? No, yeah. Seems on to be some automatic. But it's essentially say, what is the easy thing? The easy thing is if you think about what you know about particles or about a particular system. Now we take the proton as an example. You know some things that you can easily get, the mass. You put it on a scale and you read off that it has a particular mass. I mean, that's something you can do. You find that the proton and the neutron have slightly different masses. I mean, you have to do a little bit more work than just take a scale, but I mean, you can imagine that you can do these measurements. Nice thing is that mass actually is a very global property in the sense that it gravitates, and so you can do some things. So of course you have to do here more complex things and get masses and charges together by moving the thing to a magnetic field or a spectrometer, and find some things like this. But you have to do, and there you see charges also at some point come in. So these particles are charged, and you already have, imagine history books, it takes a lot of effort to get these things, to get the E over M and that sort of thing. So don't forget these things that what we know, it's either simple global properties. Spin is another property. I mean, at some point you have to convince yourself what is the spin of the particles. Now, for the proton, spin 1/2. I mean, it's built in a whole formalism of quantum mechanics that you need spin, you need fermions, you need bosons, etc. But this is one of the particles which has the smallest spin possible, just as electrons. It has a magnetic moment. There again, you see there already numbers come in which have not only these digits, but in principle have many digits, but still are numbers. And somehow this must contain some information. And of course, this is already the first part where you know that on a proton and neutron, it has tremendous amount of information hidden in there. For instance, the fact that Gn, it's a neutral particle. But it does have a magnetic moment. Magnetic moment is almost as big as that of the proton. A factor minus 2/3 of the one of the proton. So there must be some structure. I mean, that's already, of course, what in the previous century, in the 30s of the previous century, people have discovered and got easily, proton and neutron. They are not as simple as an electron, for which G is 2, rather than this number. And then 2, it's really 2. No, it's not really 2, it's 2.000, and then there's something coming. And then some other things come in. As you well know, field theory to calculate these things. These corrections, which Mike drew already some of the diagrams. So then you have, again, all of these discoveries, of course, are hidden in a framework of where you have to get a consistent picture. Yeah? And field theory was one of them, if you want to include here the G of the electron. And to understand it. Now then there's for the fact that proton and neutron have the same, roughly the same mass, are so much equal. And for the strong interactions they are very equal. I mean, nuclei, numbers of proton and neutron. Some of the properties don't change, their strong interactions don't change. Of course their appearance in the world changes drastically, because charge is of course completely different. So binding electrons to form atoms and whatever is a privilege of the protons that provide you the charge, the number of protons. But nevertheless, neutrons have important properties. You see atomic nuclei that are twice as heavy as the other one, and that also shows up. And then they have baryon number. I mean, that's one of the topics that Mike says. There's more. There's several things of baryon types of baryons. And then essentially this simple structure comes to mind. I mean, it dates from the 60s in the previous century. That we build it up in a very simple way from some constituents. Of course, that was already immediately implemented in the 30s. People could have gone to know this already, because you see this G, which is not 2, but then you needed field theory, so that was not yet in the 30s, but in the 40s, 50s, people started realizing it. Building accelerators, doing experiments at SLAC, and finding that the proton indeed is not a point particle, whatever that is, but is a big blob, 1 femtometer, and it has a beautiful charge distribution. And indeed, the neutron had a similar charge distribution, very much similar. And I mean, this has been verified to enormous precision, thanks to also, for instance, experiments in the facility JLab where Mike is. I mean, there the best measurement of the proton and neutron form factors are now there, and we have them to tremendous precision, and we start worrying about how equal are they, or how different are they, and where are they different asymptotically in the small region. And of course they are different because the charge adds up to 0 or 1, so they I'll come to interpretation of those things as part of my lectures. So that's That's what I call global properties. And then there are a few things where you can say, and now let's start in more detail to a composite system. And one of it is, give it a real look. And a real look is, of course, photons. So shoot photons on it, and indeed, what you see is you shoot photons on it, and depending on the energy, you suddenly see this spectrum arising, which Mike had here on the blackboard. He had this spectrum of resonances showing up. And that, of course, yeah, it's completely consistent with the picture that you have at some point if the measurements at SLAC showed that the radius is 1 femtometer. Everybody knows that who knows a little bit of quantum mechanics, that then wave numbers come in like pi over r, and pi over r, and or 1 over r, let's take it as a scale, the 1 over r scale, 200 MeV. And indeed, at a few hundred MeV, you had the first resonance, and etc. So it's not strange. I mean, that's precisely what you want, and how you investigate this whole system. So perfect. That's there. So that's something I will not discuss in any more detail. This is another thing that we will not discuss in much more detail, but of course, knowing that there are things going on, you can have other ways of looking at the proton or neutron or whatever, and not using photons, but for instance use the other gauge bosons, even if you didn't know that beforehand. But one manifestation of the other gauge bosons is the decay of the neutron into a proton, where and then already saying we know these things are composite, so you have the quarks, the change of a d quark into an up quark, the emission of a W, and then the production of an electron and a neutrino. That's another have a look, which like a real look where you see the charts and the excitation energies. Here you also see information, and one thing, you see a number, not G, which is this 5.7 or something, but you see another number coming in, which is characteristic of some structure of the proton, which is then known as the axial charge. Yeah, and it is in some way 1.26. And again, if you had quark models, you would expect naively, but that's like charges 2/3, you know, adding 2/3 and 2/3 and minus 1/3 gives you charge 1. If you do similar sort of calculations, simple calculations, you probably have done it in your quark model. What would you expect for GA? It's not 2/3 plus 2/3 minus 1/3 is plus 1. That's the charge of the proton. And then for the neutron, you know, you can get charge 0 with 3 quarks. So what would you anybody knows the number that you would get if you do this in the most naive way? I will not discuss that anymore in the lectures, but it is the number 5/3. It has also something to do with spins, so you measure with the spins. So it's essentially decay of a spin 1/2 particle. So you would expect 5/3. You don't. It's not too far off. It's not 1.7, but it's 1.3. But at least it's. I mean, that's with many of these properties where we had as a global look, we could understand it. The G is 2 points. What was it? 5.5 or so, rather than being, most naively, you might want to expect there 6 or so, if you do some quark counting, with spin 1/2 and whatever, and you would have -4 for the neutron, and now you go back, and what you found is essentially you went back to, I go back to this magnetic moments. -4 and 6, and in the same way you would have expected here on simple, writing down the simplest wave function, which we are going to do anyway in a minute, but then I'm going to focus more on momentum dependence, that you would expect here 5/3. Okay. We can discuss in the afternoon more details if you want on these sort of things. Now, That's what I called real looks at proton, where you see something explicit. And then the nice thing is that you can also have what is a virtual look at the proton, as call it. And then your photon is produced either with a pair or it is exchanged from an electron. And as being an exchange particle, in both situations, it need not to be a real photon, so it doesn't need to have q squared equals 0. And this q squared then is going to be one of the variables in the exchange variable. That was already also mentioned in the 2-to-2 process. You do not only have the total energy, but you also have the exchanged momentum, the s and the t variables, which were discussed previously. And here you see an exchange variable q. And indeed, q squared is like the t in any 2-to-2 process is negative. That was also in Mike's talk. So that's so you can measure negative q squared or positive q squared. I mean, if you produce with an electron-positron annihilation, if you produce energy and momentum, that energy and momentum better satisfies a condition that q squared is positive. Energy is larger than the momentum of that pair. And so it's positive, and if it's positive in one frame, you can look at it in the scattering process as you wish, then it will always be, of course, positive, being covariant. So that momentum exchange can be positive, negative, and as such you can start measuring structure, and that structure is precisely what is for positive, for negative q squared, which is space-like. I use a metric always that the metric, the time is +1 and the space is -1, so my metric is always space-like, is negative q squared. That negative q squared space-like dependence reflects something. And that I'll come to in more detail. It reflects the distribution of charge in the space-like charge distribution. So it is somehow the form factor of the wave function in x space, absolute value squared. And this thing actually is something which is time-like, and it's precisely what does it reflect. If you really look at it, E plus, E minus, it can reflect, say, the production of particles like a rho or whatever. But of course, in this process, you're bound to constraints. Precisely the constraints in the STU plane that Mike had mentioned to you. In this case, there is the S. If you really look at E plus, E minus to n bar, you need at least to have here sufficient energy to produce this, and then don't produce them with any momentum. So that's the threshold, and so 4m squared is one of these thresholds. It's one of these regions where you enter along a particular direction, in this case q squared, the physical region of this E plus, E minus to n bar process. Yeah? So that's a time-like form factor. And you can measure these, and that's what I wanted to illustrate here. That's a point that Mike also did discuss in great detail. In principle, this is one function as a function of this q squared considered as complex variable. The t variable, if you want, in this sort of process, or the s variable. Yeah, that, or if you call it s or t, that depends on how you look at this triangle, in which process you are looking at the physical process. I mean, these are, again, precisely two examples of these crossed processes that Mike discussed. And there's, of course, a third one, which you can have. But in this case, since these two particles are identical, the SU crossing would give you one identical process. So two would be identical and one would be an annihilation process. So that's this part. So that's what, and this one I will then come to in a minute. Let me show you. This one I do want to show you is already had these beautiful examples of proton densities and neutron densities with these are not the latest result of JLab, but they are more, and they show you certain things. Now, that's for now what I want to show here, and then what I want to do next is to start doing on the blackboard to look at a little bit more detail how you can start doing these sort of wave functions that I want to look at. So what do you want to really then get, for instance? Now, and I'll do that now in two ways. So what I'm going to do is I'm first going to look at it as being a system of quantum mechanics. So I have a phi n of x, and I have a phi n of p, or I will look at it in either way or another, at a momentum space wave function or as a coordinate space wave function, and then just consider as if we are doing quantum mechanics. And then the second thing is we are looking at quantum field theory. So how are we doing then? And then the wave functions, yeah, I mean, it would be simple if you say, I mean, here the simplest wave functions are e to the I px. Let me not worry if it's one-dimensional or three or whatever dimensions, but it's plane waves. And here, of course, you would say, but I know how to do this. Our plane waves are either plane waves for spin 0 or they are spinors for, and that's actually also in quantum mechanics. Now, then we add a 2 component, and now here we have to add a 4 component, and those are the details of quantum field theory. In some sense, yes. You can make already this analogy and see sort of how you can, in particularly dealing with composite objects, and I'll take 2 examples, nucleons in a nucleus or quarks in a nucleon, how you get, say, just matrix elements of, and in quantum field theory, matrix elements of fields, and in quantum mechanics, it's much easier to work with quantum mechanics. That's sufficient. I mean, pair creation is not really an issue, and so you usually work with, say, products of wave functions, consider them, make them antisymmetric, Slater determinants, whatever. And of course, you are stuck with problems like multi two-body or three-body correlations and that sort of stuff. So let's see how you do this. So let me start off with the simplest situation, which is this quantum mechanical situation. And already there, you see that it's, I mean, a system is not necessarily just a product of wave functions. I mean, for an atom, it works pretty well, that the electrons, and that is, you have a configuration in an atom, complex atom, 1s squared, and then 1s squared 2p, or 1s 2s first, and then a 2p, 2s squared, 2p squared. That's the configuration of the carbon atom. And so you know these products of wave functions, they seem to work rather well. For a nucleus, now actually it works amazingly well. I mean, for a nucleus, you also have the sort of magic numbers of nuclei really tell you that you are filling levels in this case in a slightly different potential. It's b is a square well or some more, yeah. I mean, there are beautiful nuclear models. A potential that you can fill up and that you can have certain levels. And indeed, the product of wave functions is, as a zeroth order approximation, not that bad. But that actually, their nuclei immediately teach us something that how would you even in quantum mechanics have to look at this wave function? And this is also what we'll discover then in a minute, in what that we can generalize in a very straightforward way to looking at quarks in nucleons. That is, of course, we have a nucleus, say with a momentum p and a given mass m. That's the nice thing. The composite system as such, those quantum numbers, you know, for those who did your Poincare symmetry implemented it. P squared being m squared, so m and the momentum, say 3 components of the momentum, px, py, pz, is really what identifies the quantum numbers of a system in its center of mass. Of course, the next thing comes in, j squared of the whole system, the composite spin comes in, and its component comes in. Those are the 2 additional ones. So you may have also 2 spin quantum numbers. You may have additional global quantum numbers like charge. But that sort of finalizes it, the global quantum numbers. So you're there. That's your system. So we know that system. So what does that have to do with wave functions with which you describe the thing? So in this case, you have a nucleus. You have your wave functions of your nucleons in it. So you want to start doing it. Or before, of course, even things like black holes don't have too much more than that sort of quantum numbers. I mean, they also have a mass. They have a charge, you know, and that's mostly it. Yeah, they have a spin. And then you, I mean, that's Lorentz symmetry, yeah? Poincare symmetry. So that's this thing. So what are you doing? You're usually measuring things by, say, knocking out something with a photon. The photon couples to a constituent. Now let's forget about that nucleons are composite, so it couples to the charge of a nucleon and throws out the nucleon. And in this way, you have in principle something like that you have an annihilation and a creation operator that create plane waves. You can do that in quantum mechanics. That's not a problem. I mean, if you want a dagger p is the state p, which if you want in x space has a wave function e to the ipx. So you have this, and then of course what you are left with is that you have some system left, and that is say a system with mx and px. So that's what you are left with, and that's in fact sort of the amplitude on absorbing a photon, and you can measure something on this amplitude. And you see a plane wave coming out. If you do it with sufficient energy for the photon q, you see a plane wave coming out of the system with p plus q, knowing that the photon has transferred a certain momentum q. You know you can work back and see that that you have some information on taking out a constituent with momentum p. If you want, I can do this by doing somewhat more details, saying that the charge operator is essentially nothing else than an integral over doing p and essentially producing, taking p out and doing this with that the charge of say some constituent n, proton, neutron, is essentially doing this and taking out this state. And this would be the momentum representation of the operator that with which a photon probes the system. Again, let's stay very general, because I want to do now some of these x and p statements in more detail. Of course, all of these things have to be refined. So that's this thing. So that's in quantum mechanics, and let me now see the... yeah, let me take this away, because in quantum mechanics then of course you're not measuring this amplitude, you're measuring something more in detail, and one of the things that you could be measuring is essentially the square of this amplitude. So you can measure this, and then the square is the a dagger p, and you measure essentially this mp. So this is what you measure, and you may not be able to you measure that the proton comes out. So you're not measuring, for instance, all the junk that comes out. So you have to integrate over dpx over whatever you use as phase space, 2 pi whatever d3px or whatever. You have to sum over whatever comes out, and this is the object which indeed people are working with. and have some powers of 2 pi to normalize things, but essentially this squared matrix element. And it's precisely this thing which indeed is a spectral function which is really coming out as EM and P. I called it P here, essentially. That is this property of the operator. So this is it. And of course, you know that these things are related to this, so this comes out, and it comes out with a delta function. And you know that the delta function is essentially, yeah, okay. Usually what you do is you write this down. You say, see, if I generalize it and write down here an AP primed, I know that P primed minus P, this has to be, this is the square, this is the right thing that comes out. And I mean, it's the AA dagger operator that is put in with here. You see that you have an AP, you have so now let me take this as definition of spectral function. I anyway go back to it, and I come to the more precise definitions of this later. So it's like from these matrix elements, and let's not worry about this delta function here now, that you start saying, and now I find. Then you look at these beautiful pictures that people who measure these, what is called spectral functions, produce, and they see as functions of energy. I mean this, now let me nevertheless put this as EM, P, so you measure this. Let me not worry about delta functions precisely. So you look at this thing, and what do you see is, oh, this EM, that's the energy, and essentially this EM can be written as essentially the mx, the m of the, let me get the minus signs right, mx plus m minus the original m, and that's precisely what you see is, you see certain mx coming out, and okay, that reflects itself is that the energy and the momentum of the absorbed photon, only at very specific energies, you see something, and you see a spike. That spike corresponds to knocking out a 1s proton, or a 2p proton or a 3f proton, whatever protons are available in these orbits. And in the ideal case, these are spikes. Of course, in any, I mean, some things, the levels may not be stable, so they are widened, and that sort of things. But in principle, you can get some information from it, and the P dependence then precisely goes this. And so at some point, you have a possibility to measure these things. If you look at people who do this, who determine these spectral functions in nuclei, and I mean in the organizing committee, there are people who know this much better and can explain this in much more detail, but you can get sort of really in those systems. And for electrons in atoms, it's even better. I mean, there you can just map beautifully the wave functions. For nucleons in nuclei, it becomes already tricky, and later on relativity starts playing a role. You have to be much more careful in how your energy of your photon, I mean, how it translates really to, this is a nucleus with A nucleons, and this with A minus 1 nucleons. And so this spectrum, how does it really precisely is? And to get the mx or whatever, better do recoil mass corrections and do all of these things. So determine and get all this information on which level are you really measuring. And then you get also there, you get particle, antiparticle corrections. But that's because, not because you are creating an antinucleon, no, but because you're missing a nucleon, and that also affects the whole potential. And so you work with particles and holes, which are missing nucleons rather than antinucleons. And those effects certainly all have to be taken into account. So a whole field of nuclear physics is there to help you. But then you have these things, and now you can start worrying. How do we at some point connect to certain properties that we are measuring? And then I want to come back to this simple wave function. This simple wave function, suppose that you from this system are able to get this thing. Now then, this wave function between the system is able to measure you at some point, for instance, the FNQ, that's the information which you are. And then if you see this, you already see it in front of you. What are you measuring? You are measuring just indeed the dp. You are measuring the phi star at p plus q, and you have the phi at p, and this is essentially your form factor which you then put in. So you measure this thing, a sandwich between this, and of course this is not what you measure. In your cross section you measure this Fn squared. So you measure essentially part of all these measurements. They give you essentially a cross section which is proportional to a sum over the charges essentially of these of protons or neutrons that you get out and their wave functions. And by separating and finding and looking at the right missing energy, which determines which A-1 nucleus you are left with, you essentially say, and now I have this information, and what does this information contain? At least this, it's the squared of what is called the form factor, which is the overlap of the momentum space wave function between P and P plus Q. Now, of course, we know that these wave functions, they are simply related. I mean, phi np is nothing else than the integral dx of e to the minus ipx or plus ipx of phi n of x, and the phi n of x is of course nothing else than the dp over 2 pi. This is, I usually use, put all my 2 pi's with the p and never with the x in this situation of the phi n p. So you know this, so now you can do this, and you can see that you can write this thing in x space, and it's a fairly trivial exercise to say that it's this thing, and so that you are measuring the rho of x, so the density. So in x space, you are, sorry, there is, I miss one of the exponentials. I mean, you see, there is a Fourier transforming, there is an e to the I p plus qx here, and an e to the I minus ipx there. So what is left is an e to the I qx. And so what you see is this Fourier transform is an overlap, non-local in momentum space, or a Fourier transform of a local product of the wave functions phi n star, phi n. We should probably have a short break, or
to rest a little bit, yes, or otherwise you can continue as you like.
10 minutes, 5 minutes. No, you don't want to go out. You want me to continue? You want to go out? Few minutes. Let's take a few. Let's start again. So we take 8 minutes. We go on 12:15. We continue.
Ovviamente lì ci sono comunque persone che hanno un pensiero, anche se per fortuna tutte non lo conoscono. A un certo punto deve chiare, l'unica cosa che sto facendo quindi non faccio consiglio. Come stai? E ciò che sta compatibile,
So yeah, it's going on. That's fine. It's some gluonic poles and that sort of stuff. On Friday you will be able to understand all of that. Okay, so let us continue at an elementary level. Today at an elementary level, and gradually in the course of the week we will speed up. Or otherwise, I of course do. I will never end up anywhere. But okay, let's start easy. Here is one property that you can see. You can get something from information about a wave function being either non-local in momentum space or local in coordinate space, and then you possibly, I mean, if you measure something in momentum space and want to link it, I mean, but you link it to this local object in coordinate space. Now that's that you can actually, you often also can trace things back to information local in momentum space. That's precisely what is done with these spectral functions. As I said there, what you do is, if you are a little bit this is something you can measure, but this spectral function is essentially not measuring this object. So let me take that away. It's much more directly that you say, here what you are talking about, if you look at it at the right missing energy, if you want, you just measure essentially this thing, a local thing in momentum space. Now that's just a different object which is measured, and that's what I call it phi np, and it is phi np squared. And if you want essentially 1 over 2 pi, if I want this thing such that it's normalized that the integral over dp is 1. I only do as if everything is in one dimension. So then you have this object. Now it's not that hard to rewrite also, do some Fourier transform of this thing by putting in these two formulas. Don't know if I didn't put exercise, but I will not do it in everywhere. So if you want it and don't see immediately, ask me this afternoon. But it's essentially, you need to put in two things. Twice this thing, you put in twice this phi and p of this way. You do essentially one integration. No, you don't do any. You do it, and what you will see is that you get this thing, e to the I qb, and you get something. I mean, you shouldn't be surprised that. I mean, invert this relation and see that you get phi n x squared as an integral over p of this object. And so what you see is that here you get, if you want, just p, this should be p. Is it q over here? No, it's p, IPB. And then what you see is that it's non-local in phi n star x plus b over 2. And phi n x minus b over 2. So you now see non-local, while here non-local in momentum space, non-local in coordinate space, and essentially you get this thing, except that you have to do here one step to get phi n x squared as an integral over this. Now, and that is that information. I mean, you can get information on the momentum space wave function and the coordinate wave function, and as I think most of you know well, you can get information directly. You cannot writing down a wave function phi n of x comma p. You would get a slash red strike on your exam if you would ever have written that down in your quantum mechanics classes, because of the uncertainty relation. No wave function on x and p states x comma p. I mean, should not be recorded this. I mean, that is, you know, that's nonsense. Huh? So, okay, let's take it away before some people say he's lecturing about states in XP. Nevertheless, you can, and let me. You can. Nobody forbids you to write down something like something like, and this is essentially a Wigner function. So just let me write it down and see how you can play with these Wigner functions. Wigner function is essentially nothing else than, say, something which in momentum space is a Fourier transform of some non-locality in coordinate space. Remember, there we see an example. So already remember that it is maybe useful to look at non-locality in coordinate space and then define it to be precisely as a phi star of x plus b over 2 and a phi of x minus b over 2. I mean, that's, the wave function, as you see, is a wave function in coordinate space, not in momentum space. Of course, I mean, you can do the other thing and then you are left with also in momentum space. You can now Fourier transform this to momentum space and then one of these can be undone, and it's an exercise if you want to write down that you can also do this and then see, the x dependence here tells you something about the non-locality in momentum space. So that's p plus q over 2 and phi at p minus q over 2. That's, of course, you can do a shift here in the integration to get this symmetric. That is so that is that's this thing. And now the nice thing of this thing, which you may say it's purely a mathematical object to be used, is that if you want f of p, you can do a very simple calculation and see that this thing is essentially it's 1 over 2 pi and then phi p squared. That object is equal to the integral over dx over 2 pi. I put here all the 2 pi's in there, and so that's this object. So if you integrate this over x, what you are left with is the momentum space density. Now, if you integrate this thing over, and then you don't need the 2 pi, so you want phi of x squared. This thing is the momentum integration, also with a 2 pi of this object. So the nice thing is that this thing indeed gives you either the density in momentum space or the density in coordinate space. So it's in that sense a beautiful object. Now you can start playing other roles. You can, I mean, people also have this thing. Make this thing go to B space, because sometimes this is very convenient rather than having momentum space to go to B space. Let me tell you already later on where this comes in. We are going to look at quark distributions as a function of three coordinates, px, py. Now, not pz, that's not a very convenient variable. X is much more convenient variable, as p plus over p. That will come. So you have x and the transverse momentum. Now, and this is a momentum distribution. This is where I earn my money with. This is what's called TMDs, transverse momentum dependent, and that was in the title. So that's what we want to look at a little bit. So that's a density in momentum space in the full momentum now of a quark. But in quarks, in QCD, everything is collinear, everything is along a line. So there is this additional dependence on this transverse momentum. Now people like to say, but let's do that in coordinate space. That's much easier. It's called impact parameter representation of the momentum distribution. So we will start looking at it, but now let's just see what it is. And to not make mistakes here, I'll take this and do it. So this is dp. So you do integrate over p, and later on as we use it, we will leave the x dependence and do this only for the transverse momentum, so we get an impact parameter space for the transverse momentum dependence. But let's do it here for this, because we only work in one coordinate. So let's do this, Fourier transform this, and what you find is that this is dx over 2 pi, and that it is phi star of x plus b over 2 and phi of x minus b over 2. So, of course, you wouldn't have expected anything else, as there is a Fourier transform in a non-locality, plus and minus b over 2. That's precisely what gives you momentum dependence. So it's Fourier transformed there. It is integrated over the full x. That's essentially because there's no dependence on that, and essentially you have to do it. I mean, that's how you from this thing got this object. So that's essentially the Fourier transform in that space, and so you can start playing with it and doing this sort of thing. So that's I put it in a number of exercises in those notes to. Yeah, you have to just play with it, because at some point otherwise it doesn't start living for you. But I think it's very useful to do it with these quantum mechanical examples. And I put in some exercises. I mean, yeah, I put in some exercises with Gaussians. I wanted to do some more work, but I didn't come to it. So I'll ask you to do that. If these exercises are, check this for Gaussian wave functions. Now, Gaussian wave functions are, of course, the most ultimate dull things that because Gaussians Fourier transform and they're Gaussian again, etc. So for those of you who are brave, take an example of this, and take an example where the momentum wave, where the rho of x wave function is e to the minus mu x, an exponentially decaying wave function, and do it immediately in 3 dimensions, because then otherwise you're this e to the minus mu r, which is, I think most of you know, that's a reasonable approximation for a quark and a nucleon, because the Fourier transform of this thing will become a dipole, and the dipole is essentially the form factor of a nucleon. So that may be much more interesting. So take as a wave function in momentum space in coordinate space e to the minus mu r, and then in momentum space this thing is going to be 1 over p squared plus mu squared, I think. Or I think it is, that's what it is. And the wave function squared is the square of that, so that's, and if you take that wave function twice and shift it in Q, you get your dipole and whatever. So do those examples and send me the results. Then I put those exercises, then I put it in the notes as the other examples. I asked you to do the Gaussians, which you can do as an example. Yeah? I mean, yeah, you say this is quantum mechanics. Yes, it is. But I think it's instructive. And I think it's more instructive if you do it with a wave function that looks different in momentum space than in coordinate space. Okay, so this is to get you a feel of Wigner distributions. So this is all quantum mechanics. Now, let's try to see if we can go to quantum field theory. So that was the other thing, quantum mechanics, quantum field theory. And again, I'll start off quantum field theory with because somehow in these lectures what I want to do is avoid, you will in these days not hear too much about next to leading order, or I mean everything will be leading order, not next to leading order, next to leading order. On the other hand, that's very essential. Because I'm now going to write down something in quantum field theory, and whoever did quantum field theory, you know that whatever I write down is, if you really take it serious, is infinite. I mean, so that's a problem. So you really have to work with it, except when you take it at the most naive tree level. But nevertheless, those tree-level expressions are very useful if you want to make contact to giving things an interpretation. What is it? What is it? Is it a momentum distribution of quarks that you are talking about? And so, within such a basic treatment, what I'll try to do is and what is one is measuring in deep inelastic scattering, and what is one is measuring if one measures also in addition a produced hadron, then one is measuring a quark distribution multiplied with a fragmentation function. And I'll do the example in Drell-Yen where you have a quark distribution and an anti-quark distribution. And then how do you generalize this when you have polarization around? Then you need your vectors not only to contain a p but also an s vector. What is the s vector that you see over there? Now the s vector, I already can tell you, the s vector that you see over there is just a thing that parameterizes a density matrix, at least if you talk about a nucleon. If you talk about a quark, it may be where were the spinors, UP, they were there, a U spinor. It may be one of the Dirac indices of the field, or it may be, if it's a spin 1 particle, it may be one of the Lorentz indices of a spin 1 field. So that's how these things come up. But how do you connect these parton or these indices for the partons, and what sort of functions can you measure? What are the polarized distribution functions and the unpolarized and the fragmentation functions? And then I'll give you another example where I am also where also like to play with is in a Drell-Yen-like process, particularly now at the LHC, people start worrying that your nucleon that two partons at the same time from the same nucleon interact. What are these objects? They're called multi-parton distribution functions. So I'll derive how you would really write down the basic tree-level expression in terms of fields of this object. And then, of course, what we want to see is why all these objects indeed behave in leading order, like calculating the hard process squared, multiplied with a quark distribution function, where so independently you want to square the information on how a quark is sitting there in the nucleon, and independently you do it for the hard process. Can this be done? Now, it cannot be done if you go to what is called higher twist. So what is higher twist? I also try to introduce that sort of concepts. So those concepts will all come up in the next few days. Let's try to see how we basically in field theory would set this up. And as said, field theory 0. No. Okay. Well, maybe let me do that over here by going to show you here a few, not to save time, but I mean here if it's anyway there, I can point at it, and you can stand it for another half hour without falling asleep. Okay. So I'll come back to these. See, the basic thing what you would like to do in quantum field theory is to say, you want to calculate something, and I'll show you. Let's do a calculation: quark gluon to quark gluon, and then you have those diagrams already for the squared amplitude if you don't have any loops. This is tree level. This dash indicates that you take the left-hand side and that you take a right-hand side. The left-hand side is essentially one diagram in which your quark exchanges a gluon with a gluon, or it is your quark which absorbs the gluon quark, and so it goes quark gluon to quark gluon. That's the amplitude. And now you square it, and this is the squared amplitude. And then, of course, you get more diagrams, and you get, among others, these diagrams in the squared amplitude. Then you start calculating this, and you have learned in high school how you do this. You do your calculations, and all of these external particles. For it, you use essentially U, a U spinor and a U bar spinor, depending on if they are outgoing quarks or incoming quarks, and you use epsilon mu if it's a gluon outgoing of the momentum. And of course you never use epsilon or u or whatever, because you're smart and you learned in high school also that your sum over the spins, because you anyway usually want to spin these things, so that you have this thing and that you use a relation like this, and then it's p/plus m, and then I have this for the internal particles, so that's why I use the squared amplitudes. And then in the squared amplitudes you essentially ultimately have a big trace, and p/plus m is there, and then there is some gamma and blah blah blah, and then you do this and you get all the results. Yeah, so that's what you, but then you need plane waves, but then this p would be a gluon or a quark, and these things are hidden in nucleons, so something must be happening here. So here essentially I would like to refer, like we had here this plane, we had this, what I said is, and I sort of illustrated in quantum mechanics, you have a nucleus, you take out a nucleon, and you essentially are left with something. That's essentially also what you are having here. You have a quark, you take out a quark, and you're left with nothing. That's essentially what your wave function was to start off with. Now, if this thing is not is a hadron, what you start off with is a p, and you have something left, x. But anyway, like previously in the spectral function, you're going to sum over all this x. Because at some point you hope that this thing and this thing never talk to each other again. Yeah? This works out. This only works out when the kinematics is right. So you need high energies to even think about doing this. Yeah? And then you might hope that you can do this thing with all its details, including going to loops and so independently, and collect all the other material and then make it into spectral functions. Let's call them spectral functions, just spectral functions. Let's do this. So that's one thing. Now, of course, you immediately see something which you have to start worrying about. And that's also a big part of what my lectures will contain further on. There's, of course, since the final state is x and you are integrating over that, and this is this, it might be that you also pick out one particle and pick another particle, and that leads you to the same final state x, and essentially, and this might be, you now also pick out a gluon. Of course, you may have to do something here, but also having an additional gluon entering in this process may contribute to the same final state. So you still have these same situations. Of course, you also have another problem, and we can talk about it. You have immediately colored final states. If you take out, for instance, in this thing, so you know something about these final states, that you are doing something which is shaky, yeah? And how can you do this? Yeah, okay. Then we have a rigorous way. I also will come back to that. We have a rigorous way. We call it operator product expansion, and sort of have methods of doing that. Whatever you do after we do it in this way with these matrix elements, you will see that you get the coefficients of the operator product expansion in lowest order, which is a number usually. It's mostly 1. And then no alpha S corrections, that sort of things. So that's part. So you have this. So if you want that hadrons are sources of quarks, like a free quark calculation, but then you have to start worrying about this. So that's one thing. And then ultimately what you would like, of course, is to do this thing, to sort of say, and now let me do all the squares independently. Let's do the squares independently. Now this thing squared is then our hard amplitude sigma, which does everything together, and that's the hard this thing. And let's this square consider essentially this thing, and let's take these things of the final state particles. Essentially, let's also collect them and essentially write them in this thing, and hope that this squared part is something like our S of P, or like our phi n of P. So maybe it is just a phi n of P, maybe it's just an f of P. It is a quark distribution. And yes, it has all properties of quark distributions, and you can generalize it to polarization and that sort of thing. So that's a thing. And then, then you start saying, and there's problems, and are they defined, are they portable, and whatever. And I will not answer all of those things. I think there's somebody here sitting on the first row who knows much better to see how portable these things could be, and how non-portable they are in principle when you go to TMDs, include transverse momentum, because that's hard. But there are already non-portable issues that immediately come up there, and that have to do with these additional gluons. These additional gluons can be of 2 types, and that already remember that now. They could be transversely polarized, so that's A mu fields where mu is transverse. Not, what is transverse in this situation? I'll come to that again on the blackboard in a minute. There is a fast direction of the proton. I can always define this proton and that proton to be back to back. So I have a z direction. If you have only one, essentially, then you have in lepton production, you have an electron and a proton. Or a virtual photon and a proton. So you have 2 things which are far apart in phase space. And if this happens, then at least you can consider this and that to be far apart in phase space. And then you can say, and what is happening here? I take 1 quark out of it. Now then you need already a system which says, but what is happening? What is remnant? Does it remain in the same direction? Could also split up in 2 fast directions. No, it remains in 1 direction, and you take out 1 quark, which then has only a single component along the z direction, which is essentially large, or a p plus, which is large. And then you can start working, and so the kinematics is important. That, coming back to the gluon, defines when something is transverse. If the gluon is polarized transverse and is exchanged in addition, you can show that it is unimportant. It doesn't lead to additional pieces which you have to do. So the additional gluons which are over there, you don't need to worry about it if they are transverse. If they are longitudinal, you need to worry about it. And you need to absorb them. Now that's another thing. We anyway will later on see that we need something which is called Wilson lines. Yeah, I'll come to that. So let me see if I want to say here more on this thing or continue on the blackboard a little bit. So actually the math of the spectral function is very simple. So let me do the math here. UU bar. So you have now, rather than having UU bar, which is p psi 0, you now have an x, but you want to sum over x. If you want to sum over x, then, I mean, this thing it has to have a delta function. This thing this is the u of p. That's the quark with momentum p. That's the difference of the p and the x. Only then you really have you pick out your e to the ipx. So that's this thing. So then let's look at this thing. So that's the squared matrix element. Now and then you do the same sort of thing which you have learned when you do current and go to x space. That's actually in the notes. It's an exercise. It's a standard exercise. You essentially say squared, then you put the delta function as an exponential. You do this. You remove essentially the sum over x. That's completeness. And what you are left with is this. And that's the closest to what I say is, remember, f of p was an integral over dx over 2 pi. We had phi star of x, phi star of 0 if you want. It's a non-locality. Could be minus x over 2 minus x plus, so divide it, but it's different. Fourier transform this, and that is your f over p. And that's the most natural field theoretical object that you have in this situation. It's essentially the quark fields, and now evaluated between proton states and give them some properties. But one of the things is, like ui, uj, oh, here it sits. It sits in a big trace. And that's what we are going to do with this thing. So we are not going to use this thing. We are now going to use this phi. And since it has this thing, and it depends on, say, if you do it in a proton, you can add these things. And so it has Dirac indices. And it has, say, that encodes all the spin of the quarks. It has a momentum index. And it has essentially, it tells you that it is a property of this. And it's essentially this thing. And using these matrix elements, the nice thing is that you can get a lot of information from this. And then, let me already give you the simplest answer what will come out. Now this then will ultimately, yeah, then you start looking at it, you don't know what it is. So it has some unknown features in it. Now this thing we are going to call the f of x, and why it is only x if this is x and pt. Yeah, it can be x, it can be also pt squared, but the simplest thing can only be essentially a Dirac structure which is derived from this, and that can be this momentum or that momentum. But it turns out that you can always write this momentum, small p times x times the capital momentum plus pt plus something. That I'll not sure that I come to that today, but I already asked you to look at the exercises then to do this, so that you get this. And now, as soon as you have this, and since these are proportional, it doesn't matter if you use that or that. If people would have been using this, that would be this, because the quark mass anyway we neglected. I mean, this is something which will give you results that are large. So that's the p slash. Yeah, that's what a person who would do the free calculation of all of these diagrams would use. That person would use p slash and would have used immediately this. Now, what you will see is if you look at the most general properties of that sort of object rather than UI, that the simplest thing is just a function which can only depend on one variable, namely x. And if you want pt squared, but it's going to be irrelevant because it doesn't show up in any of the traces that you have to do in the hard process. So it's if you want just a pt squared distribution, pt squared dependence, which you as well could integrate over, and then you have the collinear function f of x. So you would say you have this function. And then you start looking at these sort of matrix elements and you see their natural interpretation. You can also do things like that. You get then inequalities and triangle inequalities, and so you get bounds and see why a polarized distribution is smaller than an unpolarized distribution. Everybody would guess this because a polarized distribution is a spin up quark minus a spin quark distribution, each of them being positive definite. So the difference of that two positive definite momentum distributions should be smaller than the sum of these two. You can see that immediately as properties of those matrix elements. So that's sort of what some of the aspects that I'll do, because that shows you how easy it is to generalize these things to spins and that sort of things, and also to include then transverse momentum. And the transverse momentum, the inclusion of that is why would it be interesting? Now, because we do see in jet physics, you see azimuthal distributions. And azimuthal distributions, so you look at phi and you see certain things happening. You see asymmetries there. Now, they are not no longer due to only the collinear, so they might be due to PT. But if you look at that sort of objects and you say, let's include in the PTs, as do here d 4 psi, and have 4 momenta, including the transverse momentum, it may have some non-trivial correlation with, for instance, the transverse spin of the proton. And that's precisely what is the richness of what TMDs is. You get additional structures. And those I'm also going to treat in a more systematic way than I'm now trying to indicate you why this is interesting. Yeah. Okay, so let me show you one thing, and I'll show you that, and then I urge you to start playing here with some exercises, and those will fit very well with the one that I think Mike was giving. That's I must have here the file, this file. So let me see, there's here a discussion, and you can read about it. It's a discussion how you collect these things, in a phi, how you do this in momentum space, how you do it in coordinate space. When needed, I will do these things explicitly for a certain derivation. But again, you can find it here also. You can. There's also here a way on which might be very useful if you are not familiar. Is everybody familiar with light cone coordinates? Yes or now then read this thing, 4 vector blah blah blah. You know, minus plus, that you can have a momentum. You can write it as 0, 1, 2, 3. Or you can use minus, plus, 1, 2, where plus and minus are just, where are they defined? P plus minus is, it should be defined here in, or maybe it is, now yeah, okay, you use n0 plus or minus n3. So that means for the coordinates that P plus is P0 plus P3. And I divide it by square root 2 to get the nice factors. P0 minus P3 is P minus. They're useful. If one thing is moving very fast, either P plus goes to 0 or P minus goes to 0, because the energy and the momentum is collinear, in essence. So that means one or the other is 0. That's of course also what you see is, and then play a little bit. Oh yeah, this way, you know your Lorentz transformations are horrible, isn't it? P0 primed is gamma P0 plus beta gamma P3 or something. So in this thing, you do a Lorentz transformation, it's so easy. P plus is alpha times P plus. P plus becomes larger with a factor alpha, and P minus becomes smaller with a factor alpha. No? Alpha is then alpha, the cosine hyperbolic of this object is essentially gamma, and the sine hyperbolic is beta gamma. But that's, I mean, it should be a link. But it is, but you don't care what about the factors are. The factors are is a factor and another factor 1 over alpha. And what the factor is in a particular situation, now do that. I gave you here, there's some exercises. Do it essentially to show that you can do a boost and that you can add a transverse momentum. There is another question somewhere to show that this thing is, show that if you have something which is on shell. So write for a particle, if you write the P plus and the P minus coordinates, and introduce of course the corresponding, like n0, n1, n2, n3, which are the basis factors. You will introduce n plus, n minus, n1, and n2. N plus dot n minus is 1. And n minus squared and n plus squared are now 0. So these are light-like directions. That's the advantage of P plus and minus. I mean, if the energy is high, one of them becomes almost 0. If you have a real massless particle, one of them is 0, and the other is arbitrary. But that you also essentially see, because you can take any momentum, take the momentum along the z direction, and only need 2 coordinates, P plus, P minus, and the one is m squared over the other. Yeah. And now you can do, now you see, if you would do that in the rest frame, what would P plus and P minus being in the rest frame? M over square root 2, because there's no momentum, both of them. And in the frame where the momentum is really infinite, then one of them would be 0 and the other almost 0 and the other almost infinite. Or very large, and the other almost 0, because the one is very large. How do you get from the one to the other? Now, essentially multiply with the momentum over, see what the constant is. Do it. Play with this, look at, and do it essentially for a nucleon in a nucleus, which is not that relativistic, and do it for a relativistic particle, and see what it is. And realize that phase space, I assume some of you are familiar with phase space. Essentially what you say is for a particle on shell, you always have to integrate over d4p over 2 pi 4 if you have arbitrary momenta, but for a particle on shell you have an additional delta function, and your energy has to be positive. This is what is called phase space. Now look at the phase space in these various situations that you have, plus, minus, or 0 and transverse thing. In 0 and transverse, everybody knows that you have to everybody knows, I hope everybody knows, that you can rewrite this thing as d3p over 2 times the energy. Theta p0 there, so p0 is positive. Yeah, so that's this thing, d3p over 2. But you can also rewrite it in this way with p3, or plus and minus. You get much nicer expressions sometimes. So realize these, or you can look at it and find them. Oh yeah, we will always also work with tensors gt mu nu, which is g mu nu. G mu nu, of course, you know your 4-dimensional energy momentum tensor. what I want to do is to restrict myself just to the 1, 2. Okay, that's just 1, 1, of course, diagonal. But what you have to do is you have to subtract the n0, n0, or add the n0, n0 mu nu, and subtract the n3, n3. In the plus minus, you just have to take that cross product. You can do an epsilon with this thing and then have just a transverse epsilon. This is when we are needed, when we do transverse degrees of freedom. So familiar. So this is a section on page, in the beginning of this first section, to see what it is. And here, at the end of it, I gave now an exercise, which is show what is this scaling all about? Why do functions only depend on x or on something else? Or where do they depend on? Do that for 2 examples. So make sure that you do this exercise. If you don't want to do any of them, do this one. Yeah? See, you in some situations encounter a situation, and let's write down this first line for a nucleon in a nucleus. So suppose that I know the density f of p. I gave it here the indice as n in a nucleus, Na. So that's a 4-dimensional, if you want, it's a energy, whatever, everything is there. The only thing I know is that for some reason that I'm going to take out this thing, that I'm going to take out a nucleon. And that this nucleon becomes a nucleon with momentum p plus q, and is taken out, so it is on shell. What do you know if you have detected this? What do you know about that momentum distribution? Now, if there is no other, there could be dot, 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 there could be all sorts of process dependence, but let's look at the basis, let's do this. Then what you will find out that this thing only is sensitive to those components, the components p, which could be 4 independent components, is only sensitive to a single one, just because of just one delta function. Now you may say, how did you get rid of the rest? Yeah, of course, you see that you have that there is still the dp, so on the right hand side there is still, it's proportional to. So there is, say some integration left, but the only integration that is left is essentially, it is the pz. This distribution depends only on one variable. Show that the variable is this y variable, this is known as y scaling, and that in a good approximation is equal to this quantity, where nu and q squared are the, take the probing of this system, take this momentum. Then do the same thing, if you're not familiar with scaling, do the same thing for a quark in a nucleon. And assume, again, that this thing has 4 components, and that one of the quarks is removed from the system by something, absorption of a momentum q, and it's put on shell, if you want, or it's something is happening with it. It becomes a jet. A jet is on shell. Everything is collinear. So the momentum is squared is 0. Yeah, even what it produces. So it's taken out. And show that then you only are sensitive to one of the components, which you, if you have d4p, of course, in principle still have to integrate over, but that I should change this exercise to having here dot, 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 and then put here dx, dot, dot, dot. Only the x component is the thing that is going to be relevant in what you further on are going to do with this calculation. And what is the x? The x, trivially, because of this delta function, is this quantity. It's q squared over 2m nu. Where now you write, in this case, it's much easier to write everything, the p's and the q's, in light cone coordinates, use p plus q minus, and show that this situation, where the momenta are 0 or effectively take do it at high enough energy where q squared goes to infinity, and take these variables, and then you see naturally that you have a limit that one of the two components of q is much larger than the other. And then take the minus actually to be larger than the plus, and show that you find something like a function only depending on one variable, which is this, and that this x then represents a light cone momentum fraction. Of course, this doesn't say to have that plus has another meaning than minus. It's just my choice of what is the plus or minus direction. I mean, any light cone direction would do. So you have to choose a light cone direction because you go to high energy and there is such a preferred direction. But yeah, this is playing a little bit with it, and some of you may know all of it, some of you may part of it. If you don't know, let's discuss this afternoon or so. I think this is a good point probably to stop now and then continue tomorrow in a, I'll promise, more systematic way to start some of the things. But then you know a little bit where we are going, I hope. And you will, one of you will tell how we do this afternoon, or? Okay, so thanks.
Then there will be at half past 3 a seminar given by an experimentalist. Sorry, at 3. So, if you need extra help, please contact them before the seminar, and just to have like an appointment for for extra help. Otherwise, they will be free to go back.
Yeah. No, but yeah. Yeah. No, so if the easiest thing is that after lunch, if you have any problems, at least according to me, that you contact us at lunch or immediately after and say, I would like to hear more about this or that, and Mike the same. And then we sit with a few people together, maybe work on the exercises. And if you need the time after the seminar, we can always make appointments, or if we do it for tomorrow or whatever. Both of us will be around most of the week. Eh? Okay, I will be leaving Friday after my seminar, but yeah.
Three o'clock.